Good morning, calculus. Woo. What a great Thursday to be coming out here and getting to do some math together. I'm so excited because today we're going to be talking about section 5.3, which is inverse functions. Now, first things to note is we are not going to be talking about logarithms, at least for this section. We're putting those on the back burner for now. You'll notice that we are essentially reviewing previous topics using different and unique functions. Well, one function we haven't talked about in this class yet is an idea called an inverse function, which is brought up in Algebra 2 and in college algebra. And these kinds of functions, they have their own specific rules that will fit in with derivatives and will fit in with integration as we go forward. We're going to start by doing a brief review of what an inverse function is. And then afterwards, we're going to look at some specific cases, some theorems involving inverse functions and derivatives specifically. And then we're going to end by looking at the relationship between derivatives and new terms like monotonic and old terms like continuity. And so for today, note your homework assignment. We have page 349 slash 373, 1 through 29. Odds. 41 through 51 odds. And 71 through 93, every other odd. You'll notice there's some jumping around here. That is because there's some tech ones in the middle here that unless you have specific kinds of graphing calculators, it's just impossible to do. And not knowing which ones you have kind of makes it really tough to do those as a group. So let's start by talking about the definition of an inverse. Now, we're going to start by talking about the definition as listed in the book, but then afterwards we're going to spend more and more time talking about the more colloquial versions of a definition, the ways you can kind of think about this definition. So let's start with the first way, which is how the book defines it. So in your textbook, right here, on page 343, you have the definition of an inverse. Let's go through it one piece at a time. So first of all, an inverse function has to relate to another function. So if you have two functions, f of x and g of x, or as we'll commonly refer to them as f and g, what it states is g is an inverse if the following property is true. F of g is equal to x for every x in the domain, and g of f equals x for all x in the domain. Now, some important notes to make about this is some terminology we're going to need to discuss. G is then referred to as f inverse of x. What does this look like in practice? Well, what it means is that y and x are interchangeable. In other words, it's a function such that if I was to switch the x and the y, I would get the other function. So if g is a function and f is a function, if you were to switch the x and y's in f, you would get g. Maybe perhaps by some simplification, but it would be there. So this is the primary way to think about it, is that x and y become interchangeable. Or, if you look up above, there's a good little definition of this, right here. If you have, for example, points, like f of x is equal to the points 4, 1, 2, 5, 3, 6, and 4, 7. Then f prime, f inverse, would be a function which does the opposite. So x becomes y and y becomes x, meaning for every value you have here, I guess it should be, if we want to match the book perfectly, This should be 1, 4. Oopsie. So what would happen is every x and every y would interchange. So 1, 4 becomes 4, 1. 2, 5 becomes 5, 2. 3, 6 becomes 6, 3. 4, 7 becomes 7, 4. Every x and y become interchangeable. Now, with many functions, the inverse is very easy to find. We're going to look now over here to the left-hand side, and we're actually going to take the time to find these real quick. Because every inverse can be found through algebraic properties and substitution if you're creative enough. The only exceptions are ones with defined inverses, which is what we'll talk about next time. So let's look at the function f of x is equal to x minus 5. Well, I can think of this like y equals x minus 5. Which means if I wanted to find the inverse, all I would need to do is switch the x and the y around. So instead of y equals x minus 5, I would get x equals y minus 5. I simply invert the x and the y. That's why it's called an inverse. Now, it is not typical to leave it in this kind of form because we do not like x being by itself. We want particularly y by itself. And so we would do basic algebra like adding 5 to both sides. Take this new function, x plus 5 equals y. And this would be f inverse. So if this is my f function, this is my f inverse function. Compare that to the second one, b. My f of x is equal to 6x. Well, what's the inverse? Well, we simply view this as y equals 6x. We then invert. So everywhere there's an x becomes a y. Everywhere there's a y, it becomes an x. And then we solve algebraically. I would divide both sides by 6. I get x over 6 equals y. Once y is by itself, we call this f inverse. So if this is my f function, this is my f inverse function. See? Same thing. If I have f of x is equal to x over 2. If I want to find the inverse function, I would simply take that function, y equals x over 2, and invert it. So it becomes x equals y over 2. And then multiply both sides by 2. I end up with 2x equals y, which means 2x would be the f inverse function. A couple more. D. F of x is equal to 3x plus 2. So, to find the inverse, we would again view it as y equals 3x plus 2, and then perform the inverse, which would mean that everywhere there's a y, we turn it into x. Everywhere there's an x, we turn it into y, and then start solving. Subtract 2 from both sides. X minus 2 equals 3y. Divide both sides by 3. X minus 2 over 3, which is how I'll leave it in this particular function, is perfectly acceptable. And this would be my f inverse of x. In a second, I'll do E and F, but before I do that, I want to make sure to showcase kind of what this property, this definition of above, actually means. What it means is if I take G and plug it into F, I will end up with X only, meaning anything being added or subtracted will disappear. Anything being multiplied or divided will disappear. Any powers will disappear. Only the variable will remain. And the same if I did it the other way. So let's take a look at A now, but now we're going to test this. We're going to do F of G. Or as we can call it now that we know that G can be rewritten, this is f of f inverse. Well, what does this look like for A? Well, for A, we could take the f function, which is x minus 5, and everywhere there is an x, we replace it with the inverse function, which is x plus 5. We do f of f inverse. And you'll notice that if you simplify this function, the parentheses would drop, Positive 5 and negative 5 would cancel, leaving just x by itself, which is how we know it worked. So b, same thing. I could do f of f inverse, or as we wrote up above, f of g. So everywhere there is the f function, so which was f of x is equal to 6x, but everywhere there's an x, I'm going to replace it with f inverse. Well, f inverse is x over 6. And as you can see, if you were to simplify this, you would just get x by itself, exactly as we predicted. And even if you do it the other way, so doing g of f or f inverse of f, you'll get the same thing. Like on this top one, if I do f inverse, that's x plus 5. But if I do f inverse of f, I'd have to plug in f everywhere there's an x. And I'll get right back to x again, as expected. Same thing here. If I do f inverse of f, I will get x over 6. But remember, my x is now the f function, which is 6x, which gets me right back to just x by itself. There's no way to avoid this with these kinds of functions. If I look at c and do the exact same thing, if I do f of g or f of f inverse, everywhere in my original function there was an x, I replace it with f inverse, which is 2x. If I do g of f, I get the same thing. They all work out. Even with more complicated functions like d, it still works. Because if I take my original function, which was 3x plus 2, and everywhere there used to be an x, I replace it with my f inverse, then when I simplify this function, the 3 is going to distribute and cancel, and we get x minus 2 plus 2, which is, of course, x. And if we did it the other way, meaning we did blank minus 2 over 3, and we plugged in 3x plus 2, the same thing ends up happening. Because if we take 2 and then subtract the 2, we'd end up with just 3x on top and then 3 on bottom. The 3 and the 3 would cancel, leaving just x, as expected. This is the definition of an inverse. It's a function who, if you were to substitute it into the other function, you would end up with just x by itself. Or you could think of it in the more literal sense, it's a function whose x and y's have been inverted, meaning everywhere there used to be an x, there is now a y, and everywhere there used to be a y, there is now an x. The only difference between these two functions is that it is common in algebra to simplify one for the other. So if we do plug in x and y into their respective inverses, we then have to back solve for y, like I said, in an algebra problem. I'm going to also do E and F to showcase kind of more advanced what these look like, but this is the basic process of an inverse function. It is a function with that unique property that if I was to plug it into the inverse, it just becomes x by itself, meaning no matter how complex the function is, I can turn it into a linear function. D. Nope, we already did E. D. Let's go with E. So on E, it states we have f of x is equal to x cubed. That's a terrible 3. X cubed. Beautiful. So now, everywhere there used to be a y, we're going to replace with x. Everywhere there used to be an x, we're going to replace with y. So this becomes x equals y cubed. And then we have to back solve for y. That's going to involve taking a cube root of each side. So we end up with the cube root of x equals y. And this is f inverse. So if this is my f function, this is my f inverse function. And note, just like before, if we were to go ahead and do f of f inverse, we would do f, which is that thing cubed, but everywhere there used to be an x, we're going to replace with the inverse, which checks out, because remember, the cube and the cube root will cancel. And if you did f inverse of f. So we did the cube root of x cubed. We still end up with x because they cancel. This is just one of those properties of these kinds of functions, is that they have to have this feeling to them, is that no matter what function you're given, you can find a function which is an inverse to it, meaning it will always result in x by itself when we substitute it into itself. So, f, last one, we have f of x is equal to 4 parentheses x minus 2. I would then think of y equals 4x minus 2. Perform the inverse. Everywhere there used to be a y, I replace with x. Everywhere there used to be an x, I replace with y. Now, as you can imagine, there are oftentimes different ways to write the solution. If we think back to D, many of you guys may have looked at the solution on D and said, well, could I go ahead and break that into 2 fractions and get an answer for each piece? Yeah, it's just a different way of approaching it. It is common in calculus to get to a solution and then have a nice stopping point where you don't bother going any farther. This is another one where if you wanted to, you could distribute the 4 and start solving that way. Or you could do what I'm going to do, which is divide both sides by 4. We get x over 4 equals y minus 2. Then add 2 to both sides, so we get x over 4 plus 2 equals y. And since y is by itself, we would call this the f inverse function. And just like before, if I do my test, this is, by the way, one of the biggest things you're going to have to do tonight, is either to find the inverse or to test the inverse. So let's go ahead and showcase how to find, which we've done. Now let's remember to test. F of f inverse, we test it. So we take the original function f, 4 parentheses x minus 2, and everywhere there used to be an x, we replace it with the inverse function, x over 4 plus 2. When we do that, you can see that the plus 2 and minus 2 are going to cancel, and then you're going to have x over 4 times 4, which is going to be x by itself. Oops. Same thing over here. If I did f inverse of f, so I would do x over 4 plus 2. Remember, everywhere there used to be an x, I replace with the original function, which is 4x minus 2. And as you can see, the 4 and the 4 are going to cancel. The negative 2 and the positive 2 are then going to become 0, leaving just x by itself. These are inverse functions. They're designed to fit this particular form. Now, before we go any farther in the notes, I do want to point out this little piece of information right here. Okay, I hate you already. All right, this little piece right here. If g is the inverse function of f, then f is the inverse of g. This is a constant relationship between the two, meaning not only is this f and this f prime, but if we think of this as g, then this is g, this would have to be, oh sorry, not prime, dang it, I'm being stupid. This is f and this is f inverse. If we think of this as g, then this would be g inverse. They always have this opposite relationship to each other. Second part. The domain of f inverse is equal to the range of f, and the range of f inverse is equal to the domain of f. This is because we have swapped around the x and y values. So the y, which represents the range of one, becomes the domain of the other, and the domain of one becomes the range of the other. They have this inverted relationship. And then finally, a function does not have to have an inverse function, but if it does, the inverse function is unique. What that means is you could simplify it and all the answers would be the same. If you have one answer and I have one answer and we both claim they're the inverse, algebraically, we could make them match. They may look slightly different, like on D here, how we have, x minus 2 over 3. Yours may be x over 3 minus 2 over 3. But those are algebraically the same, which means we have one answer, a unique answer, which is a big detail. Now, to verify that something is in fact an inverse, this is an example in the text, but I'm actually going to go directly into the homework. So let's pull up a homework assignment. So, this is referred to as verifying an inverse. Inverse. let's see some homework problems. What looks fun? Okay. Show that f and g are inverse functions, a analytically and b graphically. We're going to focus on the a part of it first. So, which of these looks fun? I'm going to do number 2, and then I'm going to do number 6. Both look kind of fun. And I may even do number 8. Who knows? So, let's look at 2. We're going to verify analytically that these two are inverse functions. To verify inverse functions, you need to test the relationship. Does f of f inverse equal x? And does f inverse of f equal x? You have to test both. It is not possible for it to be one without being the other, but you need to test both. It is possible that one of these works and the other doesn't. Notice that in our original definition, we have the word and here. And indicates that both are true, which means if we want to prove it, we have to prove both of them. If it just said or, we could do one of them. But with the word and there, we have to check both of them every time. So let's take a look at number 2 and verify that these two functions will get the same results. With number 2, we have 3 minus 4x as our first function, which we're going to call f. And our g function, which we're going to call 3 minus x over 4. Okay. We're going to verify that these two are inverses. Now remember, if f is a function and g is its inverse, we could call this f prime. Remember, g could also be called f prime. Damn it, I keep using primes. This would be f, then that we're verifying that this is f inverse. If this is g, then we are verifying that this is g inverse. So let's do it. You'll find that throughout the day I will make that mistake a couple of times. I'm sorry. It's just old. Old brains farting repeatedly. Okay, so let's test it. So we take the original function f, 3 minus 4x. Whenever there's an x, we're going to plug in what we think is the inverse. And we think that g is the inverse. So everywhere there used to be an x, we're going to replace with 3 minus x over 4. And then we're going to see, does this simplify to one solution? And it turns out it does. The 4 distributes. The 4 and the 4 would cancel, leaving 3 minus x. And the double negative would distribute, so it would become negative 3 and positive x. Positive 3 and negative 3 would cancel, leaving just x by itself. It checks out. Now we do the second test. We need to make sure that the other one also works. So everywhere in the other function, 3 minus x over 4, we replace with 3 minus 4x. We need to test both, so we are testing both. So we distribute. This becomes negative 3 and positive 4x. Negative 3 and positive 3 would cancel, leaving just 4x on top and 4 on bottom. The 4 and the 4 would cancel, leaving just x. So since both of these work, f and g are inverse functions. That's it. You have to do both tests in order to verify this. Compare this to something like number 4. So we have one function, which is f equals 1 minus x cubed, and the other function, which is the cube root of 1 minus x. Well, let's see if they're inverses. So I'm going to perform 2 different tests. First test, I'm going to take the g function and plug it into f. So 1 minus, everywhere there used to be an x, I'm going to replace with the cube root of 1 minus x cubed. Now, cubes and cube roots will cancel, leaving 1 minus x. The negative would distribute, the 1 and the negative 1 would cancel, leaving just x by itself. It works. Second version, remember, always test both. I take the second function, which is the cube root function. Everywhere there used to be an x, I'm going to replace with 1 minus x cubed. Note the parentheses that I'm constantly using. It is because I don't want to forget anything that might distribute or be applied to an entire function. Always assume that the parentheses are necessary here. So 1 and negative 1 are going to cancel. The negative is going to distribute and make this positive, so we end up with cube root of x cubed. And obviously cubes and cube roots cancel, leaving just x by itself. Looks good. Since both these work, we would say f and g are inverse functions. And since it asks us to show, this is our showing. This is our work. Okay, let's compare this to number 8. 8's a little bit more complicated, but it's going to follow the same basic rules. So, number 8, we have the first function, f, which is 1 over 1 plus x. And we have g, which is 1 minus x over x. This looks fun. Let's do it. First one, I want to take g and plug it into f. So I do 1 over 1 plus, I would do 1 minus x over x. Now, these become very, very fun to do if you're not prepared for them. So what I'm going to do for this problem is I'm actually going to use a little cheating technique. I'm going to take the top and bottom and multiply them by x, which I'm allowed to do provided that x does not equal 0. And you'll notice for this function, we're assuming that x does not equal 0 for g at the very least. And so that's a good start to make. Now, x could be 0 over here, but notice we're looking at the g function as the one we're plugging into. And in the g function, x cannot be 0. So we take the top and bottom, multiply by x. On top, we get x. On bottom, the x has to distribute to both pieces. So 1 times x is x, and then x times this fraction. The x on top and bottom would cancel, leaving 1 minus x. Now, the 1 minus x and the plus aren't going to do anything, so they're going to drop. 1 plus x minus x, the x and the negative x are going to cancel, leaving x over 1, or just x by itself. Oh my gosh, look at that. With some trickery, we make this thing work. If this step is a little weird, do note all we did, just to showcase again, the more expanded form. So we took 1 over 1 plus x minus 1 over x, and multiplied it by x over x. Now the x on top becomes an x. We get x plus x minus 1 over x times x. Remember, we got to distribute to both terms. The x and the x on top and bottom are going to cancel, leaving just x minus 1. Sorry. Should be 1 minus x. I made a mistake right there, but I hope you see where this piece comes from and how it works itself out. Let's look at the second piece. So same basic property. Everywhere we take the g function, everywhere there is an x, we're going to replace with 1 over 1 plus x. So we're verifying that this works. And just like before, I'm going to use the exact same trick. I have a denominator that I don't want to have to deal with. Fractions inside of fractions are annoying. So I'm going to multiply this by x plus 1 over x plus 1. What will that do? Well, on top, you have to make sure to distribute. So we're going to take x plus 1 times 1. And the x plus 1 and the 1 plus x, oh, I guess those are backwards, but they're the same thing. Those two are going to cancel, leaving just 1. On bottom, multiplying 1 over x plus 1 times x plus 1 is going to end up with a 1 on bottom. Leaving just x by itself. It eventually works itself out. It's just all I can say. So these are referred to as inverse functions. Now, it does say they show it both analytically and graphically. So at this point, I'm actually going to pull up my functional graph using Desmos. Let's see if I got it. Oop, there it is. Okay. Now, you'll notice that I have a function up here that I'm going to talk about here in a second. But for now, let's go ahead and take a look. I'm going to start by looking at number 2. On number 2, the graphs were 3 minus 4x and 3 minus x over 4. Now, these are referred to as inverse functions if the following is true in the graph. So this is your next piece of notes. Pulling out a new page notes for myself. This is referred to as the reflective property. And there's two variations on this. There's the variation with single points, or the table. And the second variation is with the graph. So, what you'll notice is, these two are just reflections across this line. This red line here, if I take the blue line and was to flip over the red line, I'd get to the green line. And if I was to take the green line and flip it over, I'd get over to the red line. An important note to make here is you'll notice a combination of points here. We have 3, 0 and 0, 3. Notice these are inverted or reflected versions of each other. And this is why, when we talk about a graph, here we go looking at our table. In the graph, the reflexive property is reflected across y equals x. But in the points, remember, we had the property of inverses, which stated that x and y become interchangeable, which means that if you have a point like 0, 3, as we did in this graph, the inverse would have 3, 0, which you'll notice it does. If I have the point 0, 3, the inverse has the point 3, 0. If I have the point 0, 0.75, then I should have the inverse point appear on the other line, which would be 0.750, which you notice it does. They always have this relationship. Whereas one exists, so does the other. And they're just reflections across this line. If I take any other point up here, like let's say I go up here to negative 1.7510, well, then its respective, the flipped version, should also exist, where it would be 10, negative 1.75, which if I go to this graph, 10, negative 1.75. They exist. With single points, this is always true. With tables of points, it's always true as well. So if I have a table like x and f of x, in this case I have like 1, 2, 3, and this is like negative 3, 6, and 12. Well, what happens is, if I then want to look at what the inverse looks like, it's going to take those same points and just switch the x's with the y's. So I'd have negative 3, 1, I'd have 6, 2, I have 12, 3. It always has this relationship, whether it be in the points, in the tables, or in the graph. The x and the y are interchangeable. The x value is 1, the y value is negative 3. But in the inverse, it's the opposite. The x is negative 3, the y is 1. And so when it asks to show it graphically, what it's asking to show is that this is always true. To show this again, I'll do the next problem, which was number 4. Number 4 had these two graphs, 1 minus x cubed and the cube root of 1 minus x. So I do 1 minus x cubed and the cube root, so there would be 1 minus x to the 1/3 power. Notice that no matter which point I choose, like let's say I look at this point right here. Where's a nice point? Where's a nice point? Where's a nice point? This one? It's pretty nice. So the point, there's not many nice points out there. Let me zoom in a little bit. Okay, so for example, on the black graph, you have the point 0, 1. And on the purple graph, you have the point 1, 0. On the black graph, you have the point, or on the purple graph, you have the point negative 1, 2. Which means on the black graph, you're going to have the point 2, negative 1. They always exist in opposite states of each other. So if you know an x and you know a y, they're going to be there. Notice that there's a place where these two happen to be the same. And that makes sense, because if I switch the x and the y, they're just going to be the same value, which is why in the picture they're the same point. But again, I can't express this enough. If there is a dot on the x, like this one, negative 2, positive 1.442, then its opposite is going to be on the graph 2. It's going to be at 1.442, comma, negative 2. So if I go over to 1. negative 1.442. What? I lost it. Going crazy. There we go. So then if I switch those values around and go to the purple graph, on the purple graph, if I go to 1.442, on the purple graph, I go to 1.442, 442, there it is. Look at that. These should have the same value, which is pretty crazy. It's just one of those things. It should always have this inverse relationship. That's the definition of an inverse. When you say something is inverted, we mean swapped around. And so when we look at this function, it's literally inverted, where x's become y's, so 0 in the x becomes 0 in y, and y's get x's, where 3 in the y becomes 3 in the x. Every x switches with every y, and every y switches with every x. On the graph, it'll always have this relationship. That's why it's helpful to keep this other graph in the picture. Showcasing now number 8 for the same reason. On number 8, this one's a little different because it's bounded by very specific regions. So let's look at 1 divided by 1 plus x as the first graph, and then the second graph as it was 1 minus x over x. Okay, so if you look at the blue line has this point 1, 0. And guess what? The red line has the point 0, 1. The blue line has the point 2, negative 1/2. The red line has the point negative 1/2, 2. Like, it's a natural relationship between these two. They're always going to have antithetical opposites. Notice that for this to work, like, it had to be bounded by some specific regions in order to get the pieces to line up well. Because if you notice, the blue line is going to have an asymptote in it, and so is the red line. You notice they have different asymptotes, but they both have an asymptote, meaning that leads directly into our next topic, which is different properties of these functions. Okay. So like before, going back to our notes, this little piece of information is contained right here in Theorem 5.6, which is right there. The graph of f contains the point AB if and only if the graph of f inverse contains the point BA. So in other words, A and B are absolute opposites. They have to fit that way. And a very simple proof of that is just by doing direct substitutions, as you can see here. This picture is one of the most important pictures in the notes. If I could copy this by hand, I would, because this is how you verify that something is an inverse function. It's because if you have the point AB on one of the graphs, the point BA has to be on the other graph. And this will always be true. If I go to a different point down here in a different location, it's going to have the same results. And it always reflects across this y equals x graph. Now, let's go to Theorem 5.7. So we're going to call this Theorem 5.6. Let's move on to Theorem 5.7. All right. It is possible for a function to not have a functional inverse. What this means is the function may have an inverse, but it may not be an inverse function. Remember, to be a function, there are rules. There are properties that have to exist. There are things that must be true if we wish for it to be a function. Every function has an inverse, but not every function has an inverse function. Okay? And an easy example of this is going to be x squared. We'll talk about that here in a moment, because x squared is unique for a couple different reasons. But for now, let's go ahead and talk about Theorem 5.7. Theorem 5.7 states two pieces. One, a function has an inverse if and only if it is one-to-one. The phrase one-to-one essentially means It has to pass the horizontal line test. Wow, I can't write today. Not that I could write any other day. Horizontal line test. It has to pass this test. So you can see over here in the example in the text, this would not have an inverse function. It would have an inverse, but not an inverse function. Because it doesn't pass this horizontal line test, it will not end up having an inverse function, which is a big detail. We care about inverse functions. Notice the theorem talks about the existence of an inverse function. It does not say whether it's an inverse, whether there is an inverse function. This is the first thing to check. If you have a graph, this is by far the easiest one. Just look at the graph and see if it passes a horizontal line test. If it does, then it has an inverse function. Okay, part 2. Now, this one's where we start to learn about a new term. If f is strictly monotonic on its entire domain, then by definition, it is one-to-one and has an inverse function. Big details there. So let's talk about a term we haven't seen in a really long time. It's not really a new term. We did talk about it like 4 chapters ago. So what's monotonic? Well, let's break it down. Mono, in this case, means one, like monocular means one spyglass. Monomial means one term, like mono in this case means one. And tonic means style or change in this case. Not like tonic like it's in tonic water. So what monotonic means is either always increasing or always decreasing. So another way of writing part 2 is actually using derivatives, because derivatives determine increasing or decreasing. If f prime of x is always greater than 0, or if f prime of x is always less than 0. It's one of those places where it's important to note the terminology, really key here. This is what monotonic literally means, is that it's either always increasing or always decreasing. So in other words, f prime is either always bigger than 0 or f prime is always less than 0. This indicates that you're going to have an inverse function, which means we can test to see if there is an inverse by looking at the graph or by looking at the derivative. So if we want to talk about how do we test to make sure there's an inverse, there are 2 ways. One, graph it. Graph and do the horizontal line test. So test to see, does it actually pass the horizontal line test or does it fail? Or 2, find f prime and ask, is it monotonic? We'll discuss more in detail about how to show it's monotonic, but for now, that's where we're going to kind of pause. So, there's an example in the textbook, which showcases kind of how to find an inverse for each one of these using both different terms, using either from the graph or from the derivative, but I'm actually going to go straight to your homework. All right, here we go. So for these ones, it's ask us to use a graphing utility to graph the function, then use a horizontal line test to determine whether the function is one-to-one on its entire domain, and therefore has an inverse. Let's look at 14. So, if I look at 14, I'm going to hide that line. 14 states we have 5x minus 3. Okay, is this function going to pass the horizontal line test? Well, yes. If we were to draw a bar going left to right and then drag it up and down, it will in fact always touch only one part of our line, so therefore it's 1 to 1. So that makes it a horizontal line test pass. There's never a time where this function is going to fail that test. Alternatively, we could also use the second test, which is to determine if it's monotonic. So on number 14, if we did it with the graph, the answer is yes, which is actually what the problem says to do. And so if we were just doing the problem, we'd be done. I want to make sure to copy this graph into my notes or into my problem so that I know that I actually did check. But even with just this, I can't. But my alternative is to find f prime. Well, if I do that, I can look at the function and see that if my original graph is f of x equals 5x minus 3, well, I can clearly see that if I take derivative, f prime is going to be 5, and 5 is always bigger than 0. This is always bigger than 0, that makes it monotonic, which means yes. Both of them pass the test. That's why it works. It's because either it passes it with the graph using the horizontal line test, or it passes it with the derivative. Now, compare this to 16 with a little bit harder derivative, which I'll do here in a second. My f of x is equal to x squared over x squared plus 4. Now, again, the problem doesn't say to do both. I'm choosing to do both to illustrate how this stuff works. So I'm going to start by doing the graph, and then afterwards I'm going to do f prime. Let's look at the graph first. So to do the graph, I need a function to be written down, so let's go ahead and go to the function. The function is x squared divided by, and on bottom, x to the second plus 4. Okay. I look at this graph. Does it pass the horizontal line test? No. Because if I was to draw a horizontal line here, I would hit it once there and once there. So again, if I test the horizontal line, like, it clearly is going to fail because there's going to be more than one place where it's going to cross. If I zoom in, it's a little easier to see. Here at -1, it has a value of 0.2, and at +1, it has a value of 0.2. It is not correct to have both inputs receive the same output, therefore it fails the vertical line, or horizontal line test. So the answer from the graph is no. What about f prime? Well, let's take the derivative real quick and see if it's actually monotonic. Well, let's take the derivative. To do the derivative, I would have to use the quotient rule, so I do low d high minus high d low, which would be 2x, over the square of what's below, x squared plus 4. So I would have to distribute, so this becomes 2x to the third plus 8x. On top we get minus 2x to the third. On bottom we get x squared plus 4 squared. We then simplify. 2x to the third, negative 2x to the third are going to cancel, leaving 8x. And on bottom we get x squared plus 4 squared. To determine monotonic, I need to determine if this is always bigger than 0 or always less than 0. And it turns out it isn't monotonic. The reason being is because the bottom will always be positive because it's something being squared. It's a real number being squared, so it's always going to be positive. But the top, if x is less than 0, the top's going to be negative. If x is bigger than 0, the top's going to be positive. And so negative divided by positive is going to be either a negative answer or a positive answer, so therefore it's not monotonic. And since it is not monotonic, that means no, there isn't an inverse function. And so there's all these different ways you can do it. By that I mean there's 2 different ways you can do it, but each one has its own unique flavors and feels to it, which is pretty neat. And as you can see, your homework fits that piece. So let's get going. We've talked about now how to show it exists, proving it 2 different ways. This example in text is really helpful for that. Let's go ahead and continue here. the guidelines for finding an inverse. This is one of the best things you can do. You notice that it basically walks through what we did on the first 5 examples. So, using theorem 5.7, determine that it will have an inverse. Do that first. Always show that we'll have an inverse first. There's no point in not doing it, because otherwise it's going to lead to more and more problems later. 2. Solve for x as a function of y, and then interchange x and y. Lastly, find the domain and range, and verify that they do work. This last step is really important, is to make sure to verify. And now, let's talk about actually finding the inverse. So, here's the inverse function for this one. This example is really great. I'm going to skip over it because I want you to be able to have it as an extra example. But for now, I'm going to now do one of the other problems we had, which was to look like one of these. Okay, I'm actually going to do one similar to the one we have up there, and one that's not similar. So I'm going to do number 26 and number 30. Okay, let's do it. 26. Boom. Okay, 26. It states, find the inverse of the function. Well, first, let's make sure it exists. Well, if we look at this, the function here on number 26 is x cubed minus 1. This is my f of x. Let's provide the first test. Does it exist? As you can imagine, since it says to find the inverse function, it will exist. But I always want to make sure to check these kinds of things just in case. How does I know it exists? Well, I could graph this thing, which is an easy option if I have Desmos or a graphing calculator with me. Alternatively, if I don't want to graph this, I could instead just find the derivative. So what's f prime? Well, the derivative of x cubed minus 1 would be 3x squared. And it turns out this is monotonic. How do I know it's monotonic? Well, it's always bigger than or equal to 0. And so this actually checks out. How do I know? Well, 3 is a positive number. X squared, since it's squared, will always be a positive number. Positive times a positive will always be positive, therefore it's monotonic. At 0, there is the chance that something wonky happens, and so I want to make sure to look at that. Because at 0 is when monotonic might break down. So maybe that 0 shouldn't be included in the other domain. Okay, so in 26, I keep going. Let's actually find the inverse. So what am I going to do? Well, everywhere there's an x, I'm going to replace with y. Everywhere there used to be a y, or an f of x as it's sometimes called, we're going to replace with x. And now we're going to solve. So I'm going to add 1 to both sides, so I get x plus 1 equals y cubed. I'm going to take a cube root of both sides, meaning I get the cube root of x plus 1 equals y. This, in theory, should be my inverse function. Well, let's see. This piece says to graph these in the same domain, so I'm going to do that. Let's go ahead and open up Desmos. So, I graph x to the third minus 1, and I graph the cube root, which is the 1/3 power of x plus 1. Boom. Okay, you can clearly see from this picture that it does in fact have this reflexive relationship over this line. You can see that they do in fact reflect across it, so this point right here matches to this point over here. These 2 points match. This point matches to this point. They always have this relationship. The big one to note here is that something weird happens right here. But it's actually okay. Both still pass the horizontal line test. So both still appear to be working. So these appear to be good functions. So it turns out that 0 doesn't look like it had any big problems to it. Although, an important note to make here is that it is very close to failing the vertical line test. Because remember, the vertical line test is the test to see whether or not it's a function. And so in this case, it's very close to failing. because right here, it's very close to failing. But then again, the original was very close to failing too. But if you zoom in far enough, you'll see that it never actually is horizontal. There's always a very tiny little gap from one point to the next point. The farther you zoom in, the more evident that is. And so this turns out is a fine function. So part A is done. Part B, graph them on the same operating coordinate. See. Part C, describe the relationship. Okay, we did that. And then D, state the domain and range of f and f inverse. So the domain for f, if we think back to the graph, the domain was all real numbers. And the range was all real numbers. Okay, whereas if we look now at f inverse, the domain was also all real numbers. And the range was also all real numbers. This one doesn't show nearly as much as the next one will. So let's go ahead and now look at number 30. And make a comparison. Okay, so number 30, same basic form. Let's just go ahead and go through it. We have f is equal to the square root of x squared minus 4, where x has to be greater than or equal to 2. Now this, remember, is a domain. So in terms of part D, I already know the domain is greater than or equal to 2 for the original function, f. I can answer the question about the range in a little bit. As it turns out, I can actually answer one more question. Because if this has an inverse, remember from one of our properties from before, it stated that the domain of one becomes the range of the other. So if this is the domain of f, it will become the range of f inverse. And it turns out it really does. Okay, let's do this. So for this function, let's go ahead and now find the inverse. Let's verify first it exists. So I'm going to find f prime. Again, not necessary. It doesn't say to show that it exists. It just says find it. So we can assume it exists, but I'm going to go ahead and do it because I want to get some good practice in. You are not forced to make this step, so please don't if you don't have to. So we do the inverse of this function, or the prime of this function, which becomes 1/2 times x squared minus 4 to the negative 1/2 times 2x. So 1/2 and 2 are going to cancel, leaving x times x squared minus 4 to the negative 1/2 power. Now, when x is bigger than 2, this will be a positive number, but 0 will not exist. Because it's a negative power, if I plug in 2, 2 squared will be 4, 4 minus 4 is 0, you cannot have 0 on the bottom. On top, if it's bigger than 0, then the top will be, if it's bigger than 2, then the top will always be positive, because 2 is positive, and everything bigger than 2 is also positive. So it turns out this is always going to be positive. So this is actually monotonic in this specific domain. Notice that that's all that matters, is it has to be monotonic in the domain in question. So now we actually have to find it. So we take our function. Everywhere there used to be an x, we're going to replace with y. And everywhere there used to be a y, we're going to replace with x. The problem in your book actually has you doing it backwards, where you solve for x and then do the substitution afterwards. I like doing it this way because this just reminds me of algebra. Okay, I'm going to square both sides. So we get x squared equals y squared minus 4. Okay. And then I'm going to add 4 to both sides. So I get x squared plus 4 equals y squared. I'm going to square root both sides. So end up with the square root of x squared plus 4 equals y. Now, important note, when you take a square root, you should always end up with a positive or negative answer. But it turns out one of these answers doesn't work. Let's go ahead and go to the graph. So I pull my graph up. Get rid of these two. My original graph was the square root of x squared minus 4 to the 1/2 power. Interesting. Okay. And my other one is the same basic function, but with a plus sign. Wow. Okay. So first thing to note here. Let's talk about the blue function. Okay. We want it to be starting at 2 in the x-axis. So it's going to start right there. Notice the y's. The lowest y value is a 0. And then it goes to infinity. Now, does it include 0? Well, if I go over here to 2, it does include 0. Okay. All right. Now, if I follow the rules, according to the rules, these two will have different answers where they flip. So the domain of 1 becomes the range of the other ones. The domain of 2 to infinity becomes the range of 2 to infinity, and the range of 0 to infinity becomes the domain of 0 to infinity. You notice that these two are just flopped versions of each other. The domain of 1 becomes the range of the other. The range of 1 becomes the domain of the other. So if one of them is easier to find, use that to your advantage. Now let's turn on the other function, the green function. And turn off the other function. There we go. Notice that this function, it has a lot more to it. But it has to be restricted because the other function has a clear starting place. It starts at 2. So you notice that this one is going to have to start at when x equals 0 in order to match that piece. If I want these two to match, like, I have to be pretty strictly bounded. There we go. Let me move the graph instead. There we go. Like that. In order to get that nice relationship between the two. I can't include anything to the left of 0 because then I wouldn't have a piece to connect it to on the right. Like if I try to pick this piece over here, negative 2, 2.87. Well, at 2.87, there isn't one over here. And so I can't include it. And remember, it has to be a function whose inverse also works. It has to be a function whose inverse also works. Which means that for this one, this function, I have to think as if my x value is greater than or equal to 0. Otherwise, this doesn't work. Now, there is a secondary component, because whenever you take a square root, there's always a negative version. But where's that one? Ah. Now, it's easy to see that this is not an inverse, because it's not reflected across the x equals y. So this is clearly not the inverse, which is why I have to look at this problem and take out that negative one. It's just the positive one that is the answer here. So, it asks what the inverse is. There's the inverse. Bounded by x has to be bigger than or equal to 0. And then asks for the domain and range. There they are. If I choose the wrong portion, it just won't have that relationship where it's reflective across the x-axis. If I don't limit the domain, then it won't either be an inverse either, because again, it won't have a matching component down here to make it work. So, there it is. That's our function. This is how you do ones like 26 and 30. Most of them are easier. These are actually the two hardest ones you have, where you have to actually do some extra work. But notice again how there's always this relationship between the domains and ranges. Even on the one before, it has that relationship. It's just harder to see because they're all the same. Right? The domain of one matches the range of the other. The range of one matches the domain of the other. It's just because these are all the same that's hard to care about because they're all the same. Over here, it's easy to see and care about. And notice that it helps to answer one of my key components, which is what's the boundaries on this piece. Because if I look at the original function, it was much easier to see that it had a defined range. And therefore, that will be easy to tell what the defined domain has to be. Okay. Let's go ahead now Go back to notes. Next part. So we did the guidelines, the pieces. Okay. Next. We got 2 theorems left. I'm going to buzz through them real quick. It's been a long video so far. I know you guys are probably getting tired of hearing my voice. But let's go ahead and look at Theorem 5.8 and Theorem 5.9. And notice they are back to back. Alright. Theorem 5.8. This has to do with continuity and differentiability. Okay, these are some parts to it. Let me go ahead and talk about each one. First thing is the givens, what needs to be found. Let f be a function on an interval I. This interval could be all real numbers. It could be a very small piece of it, but it is an interval that we're talking about because it gives you more play with what you can do with it. If I only allowed it for all real numbers, then some functions this isn't going to work for. I'd have to have more rules and more theorems. But by doing it in an interval, I actually expand how many things I can do this with, because I can do it with big intervals or small intervals or anything in between. And if f has an inverse function, now we've already talked about how to show it has an inverse. That was Theorem 5.7. But if we then show it has an inverse, the following have to be true. So it has to be a function with a domain on an interval. So that's most functions. But it has to already have an inverse. If it has an inverse, the following statements are all going to be true. First one. Okay. If f is continuous on the domain, then so is f prime. Sorry, f inverse. Dang it, I'm doing it again. So that's a big detail. In other words, continuity is free. So if you know for a fact that like your original function is a cubic function, which we know is always continuous, then guess what? Its inverse will always be continuous as well, as long as it exists. 2. If f is increasing, on its domain, then f inverses as well. And the same goes for decreasing. So in other words, in general, they're going to have the same relationship. If f is increasing, then f inverse is increasing. If f is decreasing, then f inverse is decreasing. Now, an important note to make here. The domain is this interval. And so I can look at very tiny intervals and be like, hey, on this tiny interval, f is increasing. Then f inverse will also be increasing on its tiny interval. If f is decreasing on this tiny interval, then f inverse is decreasing on its tiny interval. And the last one is the fun one, the big one. If f is differentiable, on an interval containing c, in this case c is arbitrary, and f prime of c does not equal 0, then f inverse, did it again, is differentiable. Okay, so what the heck does this mean? This is a big one, and this is the one that's kind of the hardest to understand until you really see the picture of this. Okay, f is differentiable. That means it has a derivative. And f prime cannot equal 0 for some value of c. Meaning, what this statement means, remember, is there's no critical values. Stop posting on Facebook. There's no critical values. Okay? In other words, I can't have a place where the derivative is equal to 0. These don't work. As long as there's no place in there where the derivative equals 0, then it's going to be differentiable. The reason this is the case is because what happens if the derivative is equal to 0. So let's look at that basic function that we talked about before, x squared. X to the second. Okay. This function does not pass the horizontal line test. However, if you were to restrict it to just 0 and above, it does. So what I'm going to do, let's see if I can remember how to do this. Assume x is greater than or equal to 0. Right? Right? You should remember this. Okay, never mind. I'm going to have to ask you to guess if we just look at the right-hand side. Or, in fact, let's look at an even better one, x to the third. Okay, well then, stop posting on Facebook, people. I hate you. All right. If you look right here, it clearly has a critical value. However, if we then use the cube root function, so we do define the inverse, right? So do x to the 1/3. You can see what is going to happen right here. Like, it's going to fail the horizontal line test here, meaning that it's not going to have a derivative here. And so, if we restricted it to just bigger than x, where we don't include 0, then everywhere is going to have a function. And notice that it matches all three of these components. If we assume that we're starting off with bigger than 0, bigger than 0, so right here, take a look at our function. If we look at this, is it continuous? Well, the red line is continuous, and guess what? So is the blue line. Is it increasing? Well, actually, this red line is increasing everywhere. It's continually going up over time. And notice, so is the blue line. It's increasing differently, but it is increasing. And notice on the other side, the same thing happens. Like, the red line is decreasing over time, and so is the blue line, just in a different way. And what this says is, as long as the slope never equals 0, which happens right here, then there will always be a derivative. Well, this one cannot have a derivative here. The blue line cannot have a derivative here. And that is because it is horizontal here. And horizontal does not mean the slope is equal to 0. It means the slope is undefined. So, this is a function where it happens to have this unique property. Now, Theorem 5.9 is the best. It's where the majority of your homework's fun comes from. Theorem 5.9. It states, so all the same requirements, let f be a function that is differentiable on interval I. So again, it doesn't have to be differentiable on the whole thing, but just on this specific interval. If f has an inverse. Notice again, it's bringing up Theorem 5.7 here, because we have to show, is it have an inverse first before we can use Theorem 5.9. Inverse, we're going to call it G. Then G is differentiable x, for which f prime of g does not equal 0. And then furthermore, the big one, g prime of x is equal to 1 over f prime of g of x. This right here is the big part of your homework. Because what this means is we don't necessarily need to find out what g is and then take the derivative. We can use f's derivative to find g's derivative. And there's an important consequence to theorem 5.9 that needs to be stated even farther. G prime at a value is equal to 1 over f prime of g at that value. This right here is a big detail, because this means I can avoid finding g prime if I can find g and f prime, which are usually easier. Usually g prime is a pain to find, especially if I just want one value, because if I can find f prime and then just plug g into it, then I'm done. I have the answer. It's that simple. And so when you look at these kinds of functions, this gives us a whole lot of flexibility on how we want to approach a lot of different problems. Now, what you can see right here is an example of how we use this, but I'm actually going to skip ahead to a homework problem. And this is why we have some differences here. Got some questions on monotonic. Monotonic. Now we go to 71 through 93. So 71 through 93 all deals with these, or 71 through 79 at least, deals with these f inverse prime A. And since he used that example to help us, I'm going to use this theorem to help us. Let's do it. So let's take a look at, let's go with 72. How do we use this information? How do we use this theorem? Well, we have f of x is equal to 5 minus 2x cubed. In this case, where a equals 7. Okay, first of all, I want to find not just these three components, like f prime and g. I can also find one more thing, which is g of a. I actually don't need g of a. Like this right here is an unsung hero. You do not need g to find g of a. Because remember, they're inverse functions. According to the very first theorem we talked about in this section, there is always a relationship between these two, which allows us to have this opposite relationship, where if I know I have 1, 4, I have to have 4, 1 in the inverse. So the question says, what's g of a? Well, it turns out there's no way to find it. So I'm going to split this into a couple different steps. I'm going to find f prime. So step 1, I'm going to do is find f prime. Step 2, I'm going to find g of a. And then step 3, I'm going to plug in 1 over f prime g of a. So these are going to be my steps. I'm going to find f prime first. I'm going to find g of a second. And I'm going to plug in. Now these first two can be done in any order. I kind of like it this way because I'm really good at derivatives. But these can really be done in any order. So let's do it one piece at a time. All right, f prime. So if there's f of x, I need to find f prime of x. So I take a derivative. The 5 becomes a 0. The power of 3 moves down and becomes negative 6x squared. Check. Now, I need to find g of a. Well, how do I find g of a? Well, if a equals 7, g of a literally means what value of f gets me 7. Remember, g is the inverse function. So if I want to find out what g of a is, I really want to find out what g of 7 is. So what this means is when f of x equals 7, which means I can actually use this to solve for the problem. If I want to find out what g of a is, all I have to do is find out when f of x equals a. So g of a is when f of x equals a. With these 3 pieces, I can solve all of these problems using a few steps. Ready? So I take my original fx, which was 5 minus 2x to the 3rd power, and I can equal it to 7. So this is where I take my f of that function and equal it to a. I can then subtract 5 from both sides. I get negative 2x to the 3rd power equals 2. Divide both sides by negative 2, I get x cubed equals negative 1. Take a cube root of both sides, I get x equals negative 1. So now I know that g of a is equal to negative 1. So the question asks, how do I find, what did it say? It said in the problem right here, it's find f inverse prime at a. Well, remember, g is just f inverse. So this is f inverse prime at a. So if I want to find f prime, or f inverse prime of a, as it suggests in the book, what this really means is find g prime of a, which according to our theorem, theorem 5.9, is 1 over f prime of g of a, which means I have to do 1 over f prime of negative 1. So, again, notice how I read through this problem. I need to find f prime, I need to find g of a. I did those 2 steps. Now, I have to recognize that f inverse prime of a is just g prime of a, according to our theorem. Then I just plug in, well, what's g prime of a? G prime of a is 1 over f prime times of g of a. So I plug it in. Well, I know what g of a is. G of a is negative 1. Done. And now, I then have to do f prime of negative 1. So I do 1 over, I take my f function, which is negative 6, and plug in my a. And there's f prime of g of a. It looks weird, but let's understand what this is really saying. This statement says, what is the inverse's slope at a? One more time. This is the inverse's slope at a. That's how you read this statement, in words. Inverse's slope at a. So I was able to find the slope of the inverse function without needing the inverse function. Never once did I plug this in and switch the x and y and do what I did before. Like, that's pretty cool. Okay. That was 72. Let's show a second example so we can see it one more time. This is similar to example 5 in your text, as you can see on the notes. And I'm going to do number, let's do one of the trick ones. Yeah, let's do 76. Okay, 76. We have f of x is equal to cosine of 2x, 0 less than or equal to x less than or equal to pi over 2, and my a equals 1. Okay, let's do this. All right, first off, step 1, I want to find f prime. So my f prime is equal to, the derivative of cosine is negative sine, but there's a 2x inside of it, so I got to do the chain rule. So this would be times 2. So f prime of x would be negative 2 sine of 2x. I need some bed. Okay, part 2. So there's my f prime. All right, part 2. I need to figure out what a is. To figure out what a is, I take my cosine of 2x and let it equal a, which is 1. This is my original function, f of x, and this is a. Now, I know when cosine equals 1. So when cosine of 2x is equal to 1, I can use that to help out. Cosine is equal to 1 when x equals 0. So when x equals 0, that actually happens for both these. So that's the same for both of them. Okay. Next. Part 3. I need to plug it all in. So I prime f inverse prime of a. So I want to find essentially g prime of 1. So what do I do? Well, I would use the formula 1 over f prime of g of a. So I do 1 over f prime of 0. Well, 1 over f prime of 0, so I plug in 0 into the f prime, so negative 2 sine of 2 times 0. Well, 2 times 0 is 0. Sine of 0 is actually 0. And I end up with 1 over 0, which is undefined. You might be asking yourself, okay, so that's weird. Let's look at the graph. I have here cosine of 2x. What happens at 0? Well, at 0, the derivative is equal to 0. And that's not supposed to be included according to our theorem, right? It cannot equal 0. So, if we actually graph the inverse function, and actually do the inverse function, it turns out the inverse function fails one of our tests at 0. It ends up being stripped down. So it can't be a function. And so that's the thing. Like, it's just kind of how you have to make it work, which is pretty neat. So those are your entire homework assignment and all different parts to it. There's a lot of pieces today. This ends up being a pretty long video, an hour and a half. But note, most of your homework, if you take a look at it, involves just finding your inverses. But that's the vast majority of your homework assignment. And a lot of it's algebraic in nature, which is pretty cool. The other part of it is involving using this theorem, which the theorem, use example 5 to help you. I cannot stress it enough. Use example 5 to help. It is one of the most important examples we have. Use it to help you out. Okay, that'll be it for today. Once again, our homework assignment, page 349/373, 1 through 29 odds, 41 through 41 odds, and 71 through 93 every other odd. That'll be it. I hope you guys have a good night, and I'll talk to you guys tomorrow.